What's up, people? St. Nicholas here. I've got a really good one for you today. I've got the theory of longitudinal dielectricity. These are the waves that Tesla found to be moving at pi over 2 times the speed of light. They're able to do this because they don't operate according to the laws of normal Hertzian physics or normal, Einsteinian, Newtonian physics. There will be no inverse square law because pretty much what we're doing is these waves are scalar, right? Meaning that they don't have any mass. So Tesla found that these waves were about 99.5% efficient. He actually found that once you transmitted them into the ground, on your receiver end, you're going to get more output than input, meaning that the earth, the ground, acts as an over-unity amplifier. And the way it does this is we're tuned to the earth's natural frequency, right? So the earth operates at 8 hertz. Parker is transmitting at 168 hertz. As long as your number is divisible by 8, you are on the same frequency as the Earth. So the Earth will take your wave, swish it around, enhance it, and there is no length factor. So you're going to get a huge output out of that. So this is by far the most efficient way to transmit electricity, and I couldn't tell you why it's not being done, but longitudinal waves are the future, people. Okay, this is where we need to go. This is where humanity needs to go to start, dissecting, figuring this stuff out. It makes me sick that we're not. But anyway, I'm going to go into the math. I'm going to go into the theory of all that. So please enjoy. Please download it. I worked really hard on it. It's a really good presentation. All right. Hope you guys enjoy. All right. Peace out. Love y'all. Hello, ladies and gentlemen. This is the theory of longitudinal-Magneto-Dielectric waves. Before I dive into it, I do want to preface this, though, by saying that a lot of this is summarized from Eric Dollard's work. This is a combination of his versor algebra, his condensed intro to Tesla coils, and his theory of wireless transmission. So here's a quote from Tesla to start it off. He says, "For the present, it will be sufficient to state that the planet behaves like a perfectly smooth or polished conductor of inappreciable resistance, with capacity and self-induction uniformly distributed along the axis of symmetry of wave propagation, and transmitting slow electrical oscillations without sensible distortion or attenuation." So here's Tesla clearly endorsing the idea of wireless transmission through the ground. He says that you will not experience any loss, and he actually was saying more than that. He was saying that these waves are 99.5% efficient. So a longitudinal wave, what is it? So a longitudinal wave is akin to a sound wave or a compressed wave, and the way you visualize this is that you need to, so think about if you have a slinky and you have one end of the slinky with one hand and one on the other end of the slinky on your other hand, and you're moving them back and forth. You move both ends back and forth, right? The little wave that's produced in the middle, right? That's going to be your longitudinal wave. And Lord Kelvin visualized this wave, and he felt that. So Lord Kelvin originally got this idea from J.J. Thompson, who was the first one to conceptualize it. J.J. Thompson found that, and I'll go more into this later, but he found that the longitudinal wave experienced no distortion through the ether. And Lord Kelvin said, well, hey, if there's no distortion, it's going to go faster than light. And he was right. Tesla claimed that I didn't write it down, but Tesla did state that it's about pi over 2 times the speed of light. Others have verified this as well. Professor Wheatstone is another credible source. He found it to be about 1.5 times speed of light, which is approximately pi over 2. It's not an exact number, but these waves are fast, people, okay? And the reason why seismic transmission is so efficient is because there's a few reasons, actually. So a longitudinal wave is scalar, okay? There's no mass quantity. It gets canceled out. So this wave does not follow the same type of rules as your Einsteinian physics, as your Newtonian physics, okay? It operates by different rules, people, okay? So we can do different things with it. Since it doesn't have mass, it can penetrate, Faraday cages. It can do a lot of things that other waves can't, which is why I say that this is the wave of the future, and we need to figure out how to, use these waves to do we can do anything with these waves. Anyway, so the Earth's natural frequency is about 8 hertz, and the reason why this transmission works and the reason why we're going to get more output than input is because since the Earth's natural frequency is 8 hertz, we need to make sure we're tuned to that frequency, right? So it doesn't have to be exactly 8. It needs to be divisible by 8. So Parker's transmitting at 168 kilohertz, which is divisible by 8. So you need to make sure you're tuned to that. And if you are tuned to that, like I was saying, it does act as an over-unity amplifier. So you're going to get a lot more output than input, and the distance dimension seemingly cancels out. So in order for me to get into longitudinal waves, I sort of want to open up with what AC current is, because if you don't know the true nature of AC current, you're not going to really understand what a longitudinal wave is. But AC current is a fourth root complex differential equation, okay? There's 4 solutions. There's 2 imaginary solutions, 2, real solutions. And these negative solutions are known as the reactive components, if you want to talk about it in today's terms. And the power companies consider these reactive components waste. So we're only using the decay cycle of AC current, okay? Where if you use these reactive currents, if you use these negative J's, which are, my bad, it's the square root of -1. So plus or minus -1, you get J, negative J. I will show you how to represent that on Eric Dollard's unit versor, but like I said, if you utilize these J components, you can, that's how you get free energy, people. It's in the J's. So this is the way you need to visualize electricity, okay? Electricity is not electrons flowing through a wire, okay? Electricity is it's a 4 archetype, okay? And this 4 archetype is like the Pythagoreans talked about it. They got their info from the hermits, who got their info from the gods. So this is what electricity looks like, okay? This is ancient knowledge, and this 4 archetype, it's very symbolic, and a lot of cultures have used it before. So this is what it looks like. We're gonna put our 0 axis on the full moon right here. So this is gonna be 0 in our representation. The first quarter, when the moon is halfway, is going to be 1. The new moon is going to be 2. The third quarter is going to be 3. And instead of going back to 4, people, we're going to go back to 0, okay? So it's 0, 1, 2, 3. And I have to go way more into this. This is going to be more, going more into this is going to be off topic for this lecture, but basically what you need to realize is the analogy is, so the top moons, right? So the leading and lagging moon are the reactive power. This is going to be our negative J component and J component. These are going to be the imaginary cycles. The full and new moon are going to be real power, okay? So just know that the longitudinal wave is going to represent the reactive power, the positive J and the negative J, and the transverse wave is going to represent the real power and the full real power when it's full and empty. So that's all you really need to know. We're going to get more into versors later, but just know the important thing is when you go, so when you move up a versor step, it's going to be, you're moving J, right? So we have J, let's just let J represent our constant, right? So J to the first power is going to be this reactive power up here. J to the second power is going to be on the new moon. J to the third power is going to be lagging. And then J to the fourth is just going to equal J to the 0 power. So those are our 4 archetypes of electricity. Like I said, I'll go way more into this on another video, but it's off topic. All right. So now we're going to get into the Tesla system and how I'm going to break down how Tesla system sort of utilize these longitudinal waves. So it's a big misconception that Tesla's original idea, they say, oh, Tesla invented radio. Yes and no. Yes and no. So Tesla, I've been saying this for a long time. I say this in all my videos. Tesla did not want his devices to operate as an electromagnetic or Hertzian wave. Okay, he realized that there was a lot of drawbacks by doing this, and he wanted to use the longitudinal waves. He did not want to use the ionosphere as a waveguide. That is a big misconception. I did it too. You say, oh, free energy. It just makes sense. You don't think about it transmitting through the ground, but the ground is honestly a lot more efficient, people, okay? So Steinmetz sort of backed this up. Steinmetz is the guy who reproved Tesla. He proved Tesla's, he cracked his patents. So General Electric, I talked about it on my last lecture. Steinmetz is really important. But he made Tesla's stuff engineerable. He broke down what Tesla was doing so all people can engineer it. And Steinmetz is definitely the reason why, the government knows what Tesla was doing and what his technology was, and they've been utilizing it for the last 100 plus years. They're at least 120 years advanced because of Steinmetz, because Steinmetz broke down what Tesla was doing when no one else could. So anyway, Steinmetz thought of the electromagnetic wave not as a transmission, but he considered it a loss, okay? He thought it was a loss due to hysteresis in the ether, so he did not consider it an efficient way to transmit, because it sprays energy, so you have to apply your inverse square law, the law that says that the farther you go, the more energy that decays. So the common physicist is going to say, and I've heard it about 1,000,000 times since this experiment happened, they're going to say, oh, the inverse square law, this is fake. You can only transmit about 20 feet before you lose 80% of your efficiency. Yes, if it was an EM wave, okay? So we're not gonna use an EM wave. Again, we're gonna use the longitudinal wave because Tesla's dielectric antenna. Some people I'm going to refer to it in this lecture as the capacitive terminal capacity is what it's called. Either way, as long as it's faced downward, as long as the geometry is in the right way, it will not transmit into the I think it's on the next slide actually. Yeah, so here you go. So if you take a look at the bottom one right here, it sort of acts, they're saying that it acts as an inductor, right? It doesn't transmit, it sort of just is going to reflect energy. It's going to create a virtual ground with this coil right here. So it's really important, and then you can see that, you know, the ground pole is actually the thing that inducts electricity versus your conventional Marconi system, where the energy is just radiation, essentially. You don't get any radiation from this. All right, so this is how the transmitter and receiver are shown. This is just a block diagram. Again, you got a big generator, big pulse that's being produced. That's being sent through the oscillation system in between the terminal capacity, in between that sphere, and it goes into the ground. And this is how it looks sort of in the ground. It's acting as a standing wave, and then it will reach its output. So here's how we do it. The way we create a longitudinal wave is it's all through the geometry of the transmitter. The way things are wired, the way that the coils are set up, every specific thing is done for a reason because it reconfigures the potential and kinetic energy. So if you know potential and kinetic energy, it's saying that the gravitational potential equals the work that's being done. And because we're interrupting this process, it's a cause and effect process, akin to being, you know, the time and space dimension. So you're separating those two dimensions, okay? So these longitudinal waves do not, like I was saying earlier, do not, you know, apply to normal Newtonian physics. So we can circumvent this, and this is why it needs to be studied, okay? This is unexplored territory for the people, at least. I'm sure the government knows all about it. But this right here is really important. This is how it sort of works. So this system right here is going to be your energy generator. You see you've got your capacitor spark. This is where your capacitor spark gap circuit is. Goes to the coil. So this coil right here is going to be our secondary coil. It's referred to here as the coupling transformer. It's going to be labeled with an M. That just means mutual inductance. We've got the resonant coil right here, which is the extra coil. And that's going to be mutual inductance. That's going to be leakage. And then you got your reflecting capacitance. That's representing, again, capacitive leakage. And then you got the earth right here, which is mutual induction. So our goal here is to create, what this device is doing, it's creating 3 separate standing waves. So one standing wave is going to be, so we have at one end, right, we have energy continually bouncing back and forth between the ball on top, the reflecting capacitance, and the ground. And this is going to be tuned to Earth's natural frequency. So this is going to be about 8 hertz. This is going to create a standing wave, and it's going to be supplied by the energy in the generator, in Parker's case, inside the 7.2 kilovolt, you know, thing in his input. So the energy that escapes into the earth is good because this is going to create another standing wave, like I was showing on my other slide, between the transmitter and the receiver. So this is going to be our actual usable energy. And then the third standing wave is going to be the pulsation between the energy transformer, so this L right here, and this coupling transformer. This transmission right here, the L and the M right here, this is signifying the exchange of energy between the dielectric and magnetic energy. So how do we do it, people? How do we get mass-free energy? So what we're doing here is, you know, E equals mc squared, Einstein's famous law, right? If you break that down, c is the velocity of light. That's a unit of length squared over time squared. So we have m L squared over t squared, but we're going to be converting this m into another L. So it's going to be L cubed over t squared. And W1 is going to be our reactive component. So this is what we need. This is going to be really important. We notice how the m goes away. And it goes away because, like I was saying last time, the geometry is going to, I'll show you later in the math. I'll prove it. So each wave is going to represent a different dimension. So the earth wave represents the space dimension. The inner transformer wave, the one, you know, the one bouncing back and forth between the capacitance and the ground, that's our time dimension. And then the resonant coil is going to be our extra dimension or counter space. So we need, our goal here is to make all these waves resonate. So in order to do this, we need to form a conjugate relationship. So In order to do this, we have to start with Michael Faraday. So these are his magnetic lines of force that he discovered. He found that these magnetic, he called them his tubes of force. These are essentially the ether. It's the magnetic field reacting with the ether. And the two little balls are two conducting cylinders. But he discovered the law of electromagnetic induction. So everyone knows, V equals IR, but, this is going to be broken down differently. Steinmetz used E. This is going to be Eric Dollard's Steinmetz electricity. I find it a lot simpler to use. I go back to school, so I have to, distinguish the V and the E, but if I can do it, you can do it too, people. So pretty much the law, he found a relationship between the electromagnetic force, I'm going to refer to it as EMF in this lecture, or voltage, is the amount of induction and the quickness of the alteration. So he found a relationship between the voltage, the induction, and the alteration, which is time. So we have E equals phi over T, and phi is going to represent the number of lines in this magnetic field. So you count each individual line, that's going to be your phi. And this is going to be measured in volts, so E is voltage, okay? And Faraday also found another complementary form of induction, where he named them his electrostatic charges, later renamed to dielectric lines of induction. So here you go. Here's how you visualize it. If I was confused at first too about what this is. If you take an electrical engineering, it's the electric field pretty much. They call it dielectric. This is referring to it as the dielectric field, but if you take in an electromagnetics class, they refer to it as the electric field. That's gonna be wrong, and we'll go into that later. Why it shouldn't be referred to it why you shouldn't refer to it as the electric field. So Maxwell actually came up with the only good thing he ever did was figure out the law of dielectric induction, where we have same sort of deal. So we have the Greek letter psi over T, and psi is going to be again the number of lines of the dielectric induction. And the reason why Maxwell is a rat, unknowingly, he didn't mean to be a rat, but he is, because he found a numerical proportion between magnetism and dielectricity, and this is going to be K equals C squared. So this led him to his famous Maxwell's equations that we all learned in electromagnetics, and he was saying that electric waves are identical to waves of light, therefore dielectricity and magnetism are inseparable. This is where the world went wrong, people, right here. This was a big mistake. Dielectricity and magnetism are completely different, and they're utilized differently, okay? And we need to get away from this way of thinking. So this brings me to J.J. Thompson, where he took a more physical and less mathematical approach, which I respect. I respect experimenting. He discovered that the lines of magnetic induction display major losses through the ether, and conversely, he found that the lines of dielectric induction glide smoothly through the ether with no opposition to motion. So he found, in conclusion, the dielectric lines of induction propagate much faster and arrive at the location a lot sooner than magnetic induction. And you need to understand that right there if you want to figure out what's really going on in Tesla's work. This is going to be on coil induction now. Think about what I'm talking about right now is you have a coil, right? You have a Tesla coil wound up, and this is going to be pretty much what's going on in between these coils and what's really happening. It's not just electrons flowing through a wire, it's a lot deeper than that. So basically what's going on here is inside this coil, while you have your pulse going, a complex electric wave forms consisting of two basic components. There's a transverse component and a longitudinal component. The transverse component is the component of energy that follows the windings of the coil, and the longitudinal component is the one that's parallel to the coil. So these two, so I'm going to represent the transverse as phi and the dielectric as psi. The transverse component is where they intersect at right angles. Take the cross product, they're perpendicular to each other. And actually I found this picture I couldn't find it in any of the modern lectures. I actually found it from my electromagnetics class in high school, but here's how it works, right? So K is going to be the direction of propagation, E is the dielectric field, H is the magnetic field. Again, just common sense tells you that this is stupid right here, because none of the waves, our electric field or our dielectric field and our magnetic field, are not following the transmission. It's going to be bad transmission, because they're not trying to move with the wave, they're trying to go away from the wave. So why would you try to utilize this? Anyway, you can just see that they're both right angles to each other. And this is the longitudinal component. Now, each one of these little squares right here is going to represent the space in between the winding. And you can see that the dielectric field, which is represented by these lines in the middle, and the magnetic field are on the same axis and actually unite. So right there, it has some pretty crazy implications. All right, so we're going to talk about induction in the space dimension. Before we were utilizing time, now we're not using time. So we're going to let Q, this is again Eric Dollard talk, we're going to let Q represent the total electrification measured in Plancks, where Q equals the dielectric flux, which is measured in coulombs, which is psi, and the magnetic flux, which is phi, measured in Webers. And these right here are going to be our total electrification. Like I said, we're only utilizing this phi right now. Psi is nowhere to be found. We are missing a half of electricity, the good side of electricity, the one that's actually useful. So yeah, the main drawback for modern day wave theory, like I was saying, is they only represent the path along the transverse axis. They don't talk about the longitudinal waves. And this is going to be the circuit equivalent. I've showed this on my last one, but I'm going to go in way more in depth now. So we have going this way is a transverse path, and going horizontally is your transverse path, and going vertically is going to be your longitudinal path. And you can see we got a bunch of different stuff going on. So pretty much what's happening here is, don't think of it as your conventional electrical circuit. Think of this as a very complex waveguide, okay? So pretty much what you need to know here is just what these coefficients mean. So C is the dielectric induction coefficient, transverse. K is a longitudinal component. It's going to be the dielectric longitudinal component. L is going to be the coefficient of magnetic induction, which is transverse, and M is going to be your longitudinal magnetic coefficient. So what we need to understand here is, like I've been saying, electrons are not flowing through a wire. That's not how electricity works. The work is done by unified fields on the outside of the coil, okay? Flowing through a wire is just an illusion. That's not really how it works. Electricity is unified fields. And since electrical induction is the product of the dielectric and magnetic flux, we need to explore the nature of these components and how they operate, right? So we're going to start with the magnetic flux. So you can see here, those are the individual spaces of the coil. Magnetic flux is what they're saying is it's opposite to the voltage, okay? So magnetic flux is usually associated with or it's opposite to the current. Magnetic flux is usually associated with voltage, but you can see it doesn't want to go into the current. It sort of repels. So you can see we've got pretty much, it's going parallel, but it's not going through the current component. And you can see this is represented. So this is going to be your Versor representation, essentially, on your rotational axis. This down here is going to be your vector representation, where this is going to be phi 1, and then this one's phi 2. Phi 2 is going downwards. Phi 1 is going, what's it called? It's going horizontally. So basically the phi 1 and phi 2 are going to be your transverse and your longitudinal component. Same sort of deal for the dielectric flux. You can see that it's not going in the voltage one. It doesn't want to. Same deal. We got a longitudinal component, and we've got a transverse component. So we're going to represent, this is going to be this equation, this rho equals rho 1 plus rho 2k. This is going to be how we're going to represent our complex induction. Pretty much everything that's going on inside of the Tesla coil while there's induction going on. This equation is going to represent it. So we have the Greek letter rho, and we have the little symbol on top, meaning that it's a Versor representation. So we have rho 1, which is going to be our longitudinal complex wave, and we have rho 2, which is going to be our transverse wave. And you can see that the rho 2 and the k are connected together, meaning that k is the direction of propagation, rho 2 is going to be associated with the direction of propagation. So going back to our E equals mc squared, this is for going to be electromagnetic. So we're going to break down the dimensions and what's going on. So we have W1 in this case equals mc squared. Break that down into L squared over T squared. This is measured in watt seconds or watts, same deal. And let's talk about the magnetic flux now, right? So the magnetic flux is going to be the current over the watt, or if we break that down, it's going to be L squared T times M over over psi. This is pretty much all it is how many lines it is. So it's pretty much the intensity of the field. And we're going to substitute these two equations together, and we get rho 2 equals ml squared over t. Usually it's, if everything's done right, it should be your Planck's constant. It should be 6.624 times 10 to the negative 34 watts per second. Again, that's Planck's constant. And pretty much what this is, what this component is, it's pretty much a flux of photons with the dimensions of energy and time. And the flux of photons, essentially, that's your electromagnetic wave. Now, our rho 1 component is completely unlike your regular electromagnetic induction, because if you take a look, right, but like before I was showing you the transverse wave, how they are parallel to each other, see how on this axis right here, right, this is our rho 1 axis, the magnetic and dielectric flux are going the same way. So if we combine them, we can get a sort of a boost of energy, if that makes sense. You can get a lot more out of that. And this one down here is just showing that there's no angle between them. They're akin to each other. So we know that rho 1 equals the dielectric flux times the magnetic flux, and we can combine them. This will give us a relationship. So we need to look at this Versor diagram before I go any farther. Just know, like I was saying, so this is going to be for the magnetic flux. So he's got it starting on the other side. So we're starting on the right side, and Km is going to Km to the 0 is pretty much 0. And then Km to the 1, the first Km, that's going to be pi over 2, 90 degrees. It's just your representation on where you are in the AC cycle. Again, don't forget that this x-axis is going to be your real axis. The y-axis is going to be your imaginary axis. So again, this is showing you that the magnetic phi 1 is going to be your real component, and phi 2 is going to be your imaginary or your longitudinal component. And same deal down here, just showing you the result vector. So Eric Dollard breaks this down. Pretty much how this works is you have your total phi, right? So your phi within the electromagnetic component is broken down into two components as well. So we have this Cam0 phi 1, and this is going to be our magnetic leakage. It's going to be transverse magnetic leakage. And you're going to have plus this Cam1 phi 2, which is your longitudinal component or your mutual magnetic induction, the good energy. Again, transverse is waste, it's leakage, okay? So transverse is always going to be leakage in my lectures. Now, same sort of deal with the dielectric field. So we have psi 2 going in the imaginary axis, psi 1 going in the real axis. And the equation for this is going to be your KD1 or KD0 psi 1, which is our transverse leakage, and then you have minus KD1 psi 2, which is going to be your longitudinal mutual dielectric induction. Now, notice this minus sign. Before it was a plus sign. Now we have a minus sign, and pretty much what that signifies is, take a look. So notice how the dielectric flux is going clockwise and your magnetic flux is going counterclockwise, okay? They're rotating, their fields are spinning in opposite directions, and this is what's, some people refer to it as vortex magnetism. That's all it is. It's just you're spinning, the fields formed are going different directions. So we're going to do a lot of math pretty much, and we're going to substitute pretty much equations 5 and 6 on the last slides into 7, which is the total, total electric induction. And you get this long thing right here. Notice how it's completely algebraic, but we're going to break this down a little. So all this is doing, it's just Eric Dollard simplifying the math a little. I'll go more into it later. He's just using lots of things to represent it so we don't have a million, different variables in our last equation. Now, pay attention to what these symbols mean. They're really important. So psi 1 is your longitudinal dielectric, phi 1 is your longitudinal magnetic, psi 2 is transverse dielectric, psi 2 is transverse magnetic. He's going to use Km to the n to raise whatever power to represent where you are in the magnetic versor, on the magnetic rotation. Same thing with KDN, it's the dielectric versor, and he's just know if you see 1s1, it's going to be longitudinal, 1s0 is scalar, okay? And if you see a k anywhere, k or negative k, it's going to be your it's essentially going to be your Hertzian component. It's going to be your transverse component. So 1s to the 0 is going to equal 1, which is dimensionless. ks1 equals ks3. Alright, so this is our big enchilada. This is our total equation. We have rho equals rho 1 plus ks1 rho 2. ks1, again, if we go back, is going to be our Hertzian operator, so we know that that component, row 2, is going to be our transverse component. Now, what's important about this slide is row 1 right here. So we have phi 2 psi 2 plus 1s1 phi 1 psi 1. So first of all, 1s1, if we go back, 1s1 is going to be our longitudinal product right there. We know this is our longitudinal component. But take a look at what else is going on, right? So we have phi 2 psi 2. What does this represent? It represents the scalar component. So there's no variation with respect to length or distance. Cool. Now we have psi 1 phi 1. What does this represent? It's going to represent our longitudinal-Magneto-Dielectric wave. So this wave is very important. This is our longitudinal wave, okay, people? There's no mass inside of this wave, okay? So since there's no mass, like if we go back all the way to the first slide, we know that it's the length, the units are going to be L cubed over T squared. And we can even get rid of that L because the length will essentially cancel out as long as we're tuned to the Earth's frequency. So this is a very unique wave. This is our longitudinal wave. It does not behave like I showed you about how our normal Hertzian wave behaves. Again, this is not going to operate according to your Einsteinian or Newton laws. It's going to be approximately pi over 2 times c, or 1.5 times the speed of light. Since it's massless, it will not experience any resistance inside the ground, and longitudinal waves are the future, and it has many implications, and we need to be starting to use this more, okay? So if you made it this far, thanks for listening. You can subscribe to me on YouTube. I'm at St. Nicholas or Matsukas Energies on Instagram. Again, credit goes to Eric Dollard. I summarized what his work was saying, or I tried to. Hopefully I did a good job. And thanks to Parker again for proving that this is possible through his wireless transmission. So here's my acknowledgements. All right, thanks for watching. Love y'all. Peace out.